Swayam Prabha. Digital India. Educated India.
Today we will be starting a new subject, that is rotor dynamics, or commonly known as theory and practice of rotor dynamics. And as the name implies, in this particular subject the theory and the practice actually goes together. In fact, if we see the history of this particular subject, it has been evolved through the practice and based on the experience of the field engineers or the practice engineers. This particular subject has been evolved. So, based on their experience, based on their difficulty in the industry, they were posing the problems to the researchers ki we are facing these difficulties and what are the causes of that, and then researchers, they came up with some kind of mathematical models and they predicted what is the problem and how it is evolving and how it can be rectified. If we see, let us first see the content of the course, and then we will go into the theory of that. So, this is the content. You can able to see that mainly the flexural vibration or transverse vibration is the main concern in the rotating machinery. Apart from that, the torsional vibration is also concerned in some of the cases. This will be discussing as we will go along the subject, and sometimes even the axial vibration or longitudinal vibration is also a cause of concern in the such rotating machinery. You can able to see that we have the concept of critical speed in this particular rotating shafts, and even we will be having some kind of concept of the equivalent discrete systems, in which we will be converting a bigger system to some kind of equivalent discrete systems. We have geared and branch system analysis, especially for the torsional vibration. We have will be studying the gyroscopic effect, which is very important phenomena in this particular rotating machinery that we will be studying. Apart from that, obviously the rotors are mounted on bearings. So, how the rotor and bearing interacting, that will be studying, and especially the bearings, they have, based on the different kind of bearings like rolling element bearing and fluid film bearing, they impart various types of dynamic parameter, that means the stiffness and damping, and especially the hydrodynamic bearings, they give some kind of anisotropic property that we will be studying. Even we will be seeing how it can be obtained using the Reynolds equations. Another important bearings is rolling element bearing. We will see how it imparts the stiffness into the rotor system. Generally, these are called frictionless bearing. So, the damping is less in these bearings. So, the property which these bearing carries is the stiffness. Apart from that, the rotors, they have some kind of instability. There are various ways this rotor can go into the unstable zone. We will study this in more detail. One of the example is fluid film bearing itself, which gives instability because of in this particular case we have cross coupled stiffness and cross coupled damping, and they lead the rotors into the unstable zone. And apart from that, sometimes the rotors is having asymmetric mass moment of inertia in two orthogonal directions. That also leads to instability because of the parametric excitation of the rotor. When it rotates, this stiffness changes along with the speed, and that gives some kind of there is a parametric excited vibration. And as we know that rotor unbalance is the most common fault, and we will see how these unbalance response can be calculated for various simple and complex rotors. Then we will be having the concept of the rigid and flexible rotor balancing, in which we will be studying in more detail how vibration based techniques can be used for balancing the rotors. Here we will be distinguishing what is the rigid rotor, what is the flexible rotor, and how these balancing methods are different for these two cases. Bearing dynamic parameter estimation, especially experimental estimation, is very important, because we have such models by which we can able to calculate theoretically using Reynolds equation the stiffness and damping property of these bearings. But the problem is, even if we have good theoretical model, but the parameter which it requires, like the lubricant properties, viscosity, or other property of the lubricant, or actual temperature conditions, and how it is varying within the bearing, is a problem. And because of that, even a theoretical model, if it is good, we cannot expect a good prediction from that, because the input which we are giving into that is not correct. So most of the time in industry, people do the experimental estimation of these parameters. So we will see that particular methods in more detail. Then we will see the measurement and the digital processing techniques, especially as we know that in rotating machinery, it gives whatever the dynamics are taking place inside the machinery in the form of vibrations and acoustics. So we will see especially the vibrations, how it can be measured, and what are the different sensors are there, what are the different analysis softwares are there, or what are the various techniques are there by which we can able to process these measured signal, and they can be analyzed for the purpose of, especially for the condition monitoring. And we will look into various kind of faults which a rotating machinery can have, and how they can be monitored through the vibration measurement. Just wait. Now we have seen the overall syllabus. This is the overall syllabus, but as we will go into more detail, we will be having more idea about the subject. And now let us see a brief how I have broken these lectures in topic wise, so that we have some kind of idea. Like these are the module wise lectures. I may deviate a little bit here and there, but this will be the overall distribution of the various lectures. Like single mass rotor analysis will be around 4 lectures, gyroscopic effects in rotors around 3 lectures, torsional vibrations 4 lectures, transverse vibration, which is major concern in the rotating machinery, it will take around 6 lectures, bearing property estimation, that will cover in 3 lectures, balancing of rotor, that is flexible and rigid rotor balancing, 3 lectures, then experimental bearing dynamic parameter estimation, that is 3 lecture. Apart from this, the instability, which is a major concern in the industry, that will cover in 4 lecture. Then there is a phenomena, subcritical speed phenomena, which will cover in 1 lecture. Then a very important tool, that is FEM, finite element analysis of rotor, will cover in 4 lectures, and measurement and signal processing in 3 lectures. condition monitoring we will cover in 2 lectures. These are the various references are there. Mostly these references people have they are some kind of monographs. They have done the research in their topics, that is on the rotating machinery, and these are something like monograph in which they have put all their research in a book form, and we will see as such these are not textbook like I am listing so many books, reference books. I cannot read all of them, but you can have just look into that. These are all text or reference books. There are so many books in this particular topic. These are all written by eminent researchers in this particular field. So around you can able to see 27 books are there, but mostly they are people they have compiled their research in these books. These are also some more books. Now we will see because this particular topic is not only a traditional subject, but still the research in this particular field is going on. So these are the some of the journals like Journal of Sound and Vibration, Transaction of ASME, Journal of Vibration and Acoustics, Mechanical Systems and Signal Processing, Mechanisms and Machine Theory, International Journal of Rotating Machinery, Advances in Vibration Engineering. These are the few journals where you can find the latest trend on this particular subject. And now let us see some important conferences which generally every 4 years or every 2 years people are conducting it. So like the first one, International Federation for the Theory of Machines and Mechanisms, that is called IFTOM. They conduct international conference on rotor dynamics. This conference every 4 years they conduct. Institution of Mechanical Engineers, IMECI, UK, they conduct international conference on vibrations in rotating machinery. They also conduct every 4 years. International Gas Turbine Institute, they conduct one that is Turbo Expo, ASME Turbo Expo. They conduct every year. This is very industry oriented symposium. Apart from that, the fourth one, International Symposium on Stability Control of Rotating Machinery. They are also conducting regularly these conferences. And there is another conference, International Symposium on Transport Phenomena and Dynamics of Rotating Machinery. And in India, we have one symposium every 2 times it has occurred, and now every 2 years it will be conducting National Symposium on Rotor Dynamics, NSRD. Now let us see some of the applications of these rotors in day-to-day life, or in industry, or in transport. Everywhere we will find rotating machineries, and the best part with the rotating machineries are that they contain large energy along with that. So mainly they are used for transmitting the power. So they have very high density of power, and because of this and associated flexibility in the such system, there is some little amount of vibration energy is also there. So you can able to see some of the applications here, like a fan, sewing machine, or car. In this, so many components are there which revolves, electric motor, all they contain rotating parts, or even a helicopter, you can able to see tremendous amount of power is there in their blades, not only the main blade but also the tail end blades. Now let us see how a turbine in actual industry is there. You can able to see is a huge turbine, and in this a lot of blades are there, and in this tremendous amount of the rotational energy it is generated. This is another view of the same turbine. You can able to see different stages of the blades. This is the turbine, the gas turbine in the aircraft engine. Now let us see various components of a rotating machinery. Like the first thing is the shaft, on which various revolving parts like blades are mounted. So this particular, you can able to see the shaft containing discs, blade, everything, that is called rotor. So all the parts which is revolving along with the shaft is called rotor. Either it is in the form of disc or blade or coupling, any parts which are mounted on the shaft is called rotor. And now apart from that, you can able to see the bearing which supports this revolving rotor, and it allows the relative motion of the rotor along with the stator. Stator is a non-rotating component which is either the foundation is there, that is also a part of the stator, in which this high rotational energy rotors are kept, and you can able to see that these foundations, they absorb whatever the vibration energy that comes from the rotor, and it reduces the basically vibration of the rotors. So here even you can able to see the pedestal of the bearing. Here is bearing, and there is a column which is called pedestal of the bearing, and this whole assembly is mounted on a rigid base that is called foundation. So we have three components mainly in the rotating machinery. There is a rotor, then bearing, and the foundation. See, as we will go along this particular subject, various terminology which we are using in the rotor dynamics. So first let us see what is rotor. Again I am repeating, we already seen in a turbine. This rotor is nothing but all the components which are mounted on a shaft, including the disc, coupling, blades, fan of component which is rotating along with the shaft is called rotor, and there is a stator which is a stationary part which does not rotate, and in between these two there is a bearing which allows the relative motion between the rotor and the base, that is the foundation or the stator. Now this particular rotors, as I told, they contain very high amount of rotational energy, and as a rotor dynamics analyst, as a designer of the rotor dynamics, one has to be very careful that whatever the rotational energy is there, that should be maximum, and whatever the vibration energy, because of the flexibility of the rotor or because of the flexibility of the bearing or the foundation, the vibrational energy should be minimum, because that is unwanted for this kind of machinery. Now let us see some of the concepts in this particular subject. Like as I told, one is the unbalance. What is unbalance? Let us see. Let us say we have a circular disc which is revolving about its geometrical center. Let us say this is the geometrical center of the bearing, is revolving about that point at some speed, let us say omega. If this is the geometrical center or center of rotation, if the center of gravity is also at the same place, then there will not be any centrifugal force. But if center of gravity is offset by some amount from the center of rotation, let us say G is the center of gravity, then you can see that there will be centrifugal force which will be m e omega square. M is mass of the rotor, E is the eccentricity which is distance between the C and G, and omega is the spin speed of the rotor, that is either in the radians per second or in RPM. Here we can use in radians per second. Now you can able to see when the center of gravity is offset from the center of rotation, we have this unbalanced force. So in rotor dynamics, the unbalance is defined as mass of the rotor into the eccentricity. So you can able to see this is the unbalance, and unbalance unit is kg meter. Now unbalanced force can come because of some other reason also, like if this is the center of rotation and if center of gravity is also at the same place, but if we keep a small mass in the form of, let us say, a screw, or either we put some mass here or if we cut it out from the rotor, let us say that is small mass mb at a radius r. So in this particular case, when this rotor is rotating, then also we will be having centrifugal force, and the value of that will be mb into r into omega. So you can able to see that this mb is very small mass of a screw which we are keeping at this radius r. Here this particular mass will be small as compared to the mass of the rotor. This radius will be large as compared to the eccentricity of the rotor. If we go back to the previous slide, you can able to see this mass of the rotor is large, but eccentricity is very small. Generally it will be of the order of in microns, and mass of the rotor will be in the order of around 100 kg, or it depends upon the rotor size. But here when we are talking about the keeping a small unbalanced mass, that will be in few grams, and this radius will be in either in centimeter or around the value will be large enough. So you can able to see that the unbalance is coming in this particular case because of some extra mass either we are keeping onto the rotor or we are removing it. So this is unbalance. Okay, if we extend this concept, that previous concept was for the rigid disc, that is disc which is thin, but let us say if we have a rotor of this size, which is long rotor, then here we will be having one axis about which this particular rotor we expect is rotating. There will be some support at the ends. Let us say these are some bearing support, and this rotor is rotating about its rotational axis. Now here let us say this is the geometrical center of the rotor, and if center of gravity is also at the same place, then we will not be having any unbalanced force in this particular rotor. When it is rotating, if center of gravity is here exactly at the center of the geometrical center of the rotor, there will not be any unbalanced force. But if we have some amount of eccentricity, that means if G is here, is not along with this, then if this distance is E, then we have unbalanced force. If let us say m is the mass of the rotor, unbalanced force will be again m e omega square, and this particular rotor will be having forces at bearing locations. Unnecessary force will come onto the bearing because of this unbalance, because unbalance is unwanted force. So what is the unbalance we have seen for a rigid disc case, and for the long rotor case we will see in more detail about this. But let us see what is why the unbalance comes in a rotor. Unbalance actually we do not want in the rotor because it is giving unnecessary force to the system, but it comes maybe because of during the manufacturing, when there is some tolerances in the machine components. So if we want to make a perfectly circular disc, there will be some deviation, maybe it will be either slightly oval shape or maybe some variations along the radial direction. Because of that, the center of gravity will offset from center of rotation, and that will give the eccentricity, and that gives the unbalance, the mass into the eccentricity. Apart from this, even if we manufacture the rotor perfectly, there may be problem during the mounting. When we mount the, let us say, disc onto the shaft, so when we are making a hole onto the disc for mounting onto the shaft, maybe that the hole itself is slightly eccentric, and because of that we are losing the center of gravity is away from the center of rotation. And even if we can able to make the assembly also perfect, what happens during the operation, because these rotors generally are working in very harsh environment like steam, high temperature, and like if gas turbine is there, lot of the fuel is there, and because of that maybe wear and tear will take place, and these rotors which are initially perfectly balanced, during operation you may find that they will be having some unbalance, and they give rise to unbalanced force which are unwanted. So periodically also we need to balance it. If we have commissioned a particular rotor in a industry, after commissioning we need to balance it, but periodically also because of wear and tear and other effect, the unbalance may come, and we need to balance that periodically. So again, coming back to the long rotor case, in which I have shown one kind of eccentricity, you can able to see that the eccentricity is in the radial direction, but this particular eccentricity now I am showing in slightly more complex situation, in which this is the geometrical center of the rotor. In the previous case I have shown the G at the radial position, but now I am giving the G at some offset position in the axial direction also. So we have two eccentricity, one is radial and another is, let us say, axial. So this is the z axis direction. So Ez is the axial eccentricity. Now centrifugal force will be acting at G, which is offset in radial as well as in the axial direction. This magnitude is m e r omega square. Now you can able to see, if we translate this force from G at C location, we will be having one force, magnitude will be m e r omega square, but we will be having moment also, that will be m e r omega square and momentum E z. So not only the force will come into the rotor, but also the moments will come. And now you can able to see that in this particular case situation is more difficult, because now we have moments also. If we are coming back to this particular previous rotor in which the eccentricity was in the radial direction, you can able to see that this particular rotor, if you want to balance it, so we need to keep a mass opposite to the G location here, and let us say if we are keeping a small mass mb here at a radial distance r, so this should be equal to mass of the rotor and its eccentricity. So with this we can able to balance this particular rotor. But in the second case, we have two component, one is the force and moment. So here the balancing is more difficult, and by single mass we cannot able to balance it. Now you can able to see the difficulty. So we need to have two places, two mass component we need to keep. Let us say mb1 at the radial distance r1, mb2 at radial distance r2, and these two correction masses can be used to balance not only this particular force, also the moment. More detail of this we will see as we will go in that particular chapter where we will be talking about balancing of rotors. So I am leaving it to you to think how these two masses can be used to balance this particular rotor in which the radial and axial eccentricity is there. I will be extending this particular concept further. Just wait a minute, I need some more slides. Now we will see the same long rotor, how other kind of unbalance may be there in this. So earlier we drew the rotors and they were horizontal in position, but during assembly it may happen that if this is the center of rotation, we may have the center of rotor, actual rotor, slightly inclined. So I have exaggerated this inclination. This inclination maybe will be less than 1 degree in actual case. So rotor is mounted which is slightly inclined. Here the center of gravity is there at the center of rotation, but the rotor is inclined. Let us say this inclination is at some angle phi. Mass of in this particular case, mass of the rotor is I, and diametral mass moment of inertia of the rotor is ID, that is perpendicular to the this particular rotor, not the along the rotor axial direction, but about the one of the diameter axis. So in this particular case, you can able to see when the rotor is rotating, there will not be any centrifugal force. Force will be 0 because the center of gravity and center of rotation are at the same place, but it will be having moment. You can able to see because this is inclined, there will be some force and the moment will be having value this. Now you can able to see the force is not there but moment is there, and because of this the bearings will take some unnecessary load, and to balance this again we require two masses as we had earlier in two different planes to balance this. This particular kind of unbalance in the rotor, this is generally called dynamic unbalance, in which we require two planes to balance rotors. And the next situation you can able to see when both the rotor is having inclination as well as the C and G are not at the same place, then not only will be having moment but also will be having force. So that will be m_e omega square if only radial eccentricity is there. If axial eccentricity is there, then we'll be having this particular moment as well as this moment which we already seen in the previous slides. So there will be two unbalanced moments, one this one, another this one. Okay, just now we have seen that how the unbalance can come in a rotor. These unbalanced force will give some kind of unwanted force or moments into the rotor, and when the rotor is having flexibility and it either on the shaft or at the bearing, the unnecessary transverse vibration will take place. Now let us see how a particular rotor which is having flexible shaft can have vibration. So let us say there is a rotor, or this is a flexible shaft and there is a disc. When this particular rotor is at the rest, obviously this will be with the bearing axis. This is the bearing axis, but as it start rotating, because of unbalanced force, it will try to deflect and it will be having some transverse vibration. Now you can able to see that this particular transverse vibration, when it is rotating, this particular rotor will come this side also. So it will move in a either circular path or in a elliptical path, depending upon the property of the bearings at the ends. This particular motion, now there are two motions of the rotor. One is spinning about its own axis, and then there is this vibration, transverse vibration, that is called whirling of shaft. This particular motion, let us see in this particular model. This is simple disc is there and flexible shaft is there. In this particular case, one is the rotation of this particular disc is revolving about this. Generally, this particular disc will be fixed onto the shaft. So when shaft rotates, it will be revolving along with this. And when there is unbalance, this particular disc will deform. The shaft will deform. Sorry, shaft will deform like this, and it will start. The shaft itself will be start revolving about its bearing axis like this. So not only the disc is revolving about its own axis, but the deflected shaft itself is revolving about the bearing axis. There are two motions. This particular motion, which you can able to see, is called whirling. The first one, which is revolving of the disc about its own axis, is called spinning. This is spinning motion, and this is whirling motion. Okay, this is a whirling motion. This here also you can able to see the whirling motion of the shaft. This is a particular phenomena which a rotor will be having when is having some kind of unbalance, and you can able to see that the whirling of the shaft, because this whirling frequency generally we represent as nu. In general, this will not be equal to the spin speed of the shaft. Omega is the spin speed of the shaft. But if this whirling is due to the unbalance, we expect nu is equal to omega. That is, we call it as synchronous whirl. Synchronous whirl. In this particular whirl motion, in this particular case, we have whirling frequency. That means this particular motion frequency same as the spin speed. Let us see this particular motion in more detail. Let us say we have this is the bearing axis. During whirling, let us say shaft is revolving in a circular path. Let us say this is the shaft position at one place. As let us say this is the direction of the shaft spinning about its own axis. Also it is spinning the whirling with omega. So after some time it will occupy this position or this position or this position. If we mark a point onto the shaft here, let us say this, if this condition is there, that is whirl frequency, there is the orbital frequency and the spin speed, that is revolving of the shaft about its own axis. If they are same, we expect this particular dot, when it is moving, will occupy these positions. Okay. So what is happening in this particular case? If we are sitting here and looking into the shaft, we will see that same face of the shaft will see all the time during this motion. This motion is called synchronous whirl. And in real case, when generally the earth and the moon, they have this kind of motion, and because of that we see the same phase of the moon from the earth, because they have synchronous motion. The spinning of the moon and the orbital frequency of the moon, they are same, and because of that we see the same phase of the moon. And here also we have the same situation. If we have another kind of motion, let us say when we have this whirl frequency is equal to minus omega. So this we can categorize as a anti-synchronous whirl. And in this particular case, let us see. So if we take one point here and we will try to see its location at other places, we will see that when it comes here it will be outside, when it is here it will be inside, When it is here, it is outside. Now what is happening? You can able to see that when the shaft is having one revolution from this place up, and then from here, here and here, is having the flexural of the shaft is taking place twice. In the previous case, synchronous case, shaft is having no flexural motion. So if we see in this particular case, the shaft bends for the synchronous case, and as a rigid body it revolves about the bearing axis. So this is synchronous motion, in which as such there is no bending and there is tension compression of the shaft is not taking place like this, but it bends and it revolves as a rigid body mode. That is a synchronous fault. But in the anti-synchronous world, it will be having the bending, and the frequency of that flexural motion will be twice per revolution. Now let us see more general motion in which we have nu is equal, which is not equal to omega. So in this particular case, you can expect that the shaft, when it is revolving, this is omega, and this is nu, which is not equal to omega. So for this particular case, it may take various positions depending upon what is the value, relative value of these two. So there will not be any fixed pattern of these, but it will depend upon what is the value of the nu with respect to omega. This particular motion is called asynchronous motion, and generally this motion will take place when we have gyroscopic effect into the system. This we'll see in subsequent classes. Okay. So to just to recapitulate what are the things we have learned today. So initially we started with introduction to the subject. I showed you all the content of the subject and how various lectures have been divided into various topics. Then we saw some applications of rotating machinery, and we found that to day-to-day life and also even in the planetary motions, these kind of rotating motions are taking place, and the study of this particular type of motion, the rotating motion and its dynamics, is very important, especially for machineries. And after that, then I introduced some few concepts, like one was the unbalance in the rotor, and we have seen that there are two type of unbalance which comes into the rotor. One is the static unbalance, which is generally occurs in a thin discs, and there is a dynamic unbalance, and generally in the long rotors dynamic balance are there, and we have seen that for dynamic balance we need to have two planes, two correction masses to balance that. And then we have seen the concept of the whirling motion, in which the shaft, which is flexible, when it is spinning, not only it spins about its own axis, but the axis itself rotates about the bearing axis, and that is called whirling motion. And especially due to the unbalance, that whirling motion frequency is same as the spin speed, and that particular motion we call it as a synchronous whirl. I defined the asynchronous motion also. Generally is there when there is some kind of friction or the contact of the rotor with the stator, and that try to drive the rotor in the opposite direction of its vault, and there we can have this anti-synchronous vault, and sometimes it is also called backward vault. As we will go in this particular subject in more deep these phenomena, and we will able to understand better. Asynchronous vault also I introduce, and generally these are there when we have like gyroscopic effect, or sometimes due to the bearing also, because the bearing also is having property which changes with speed. Because of that also we have this kind of asynchronous vault in the rotating machinery.